Good morning and welcome to another session on the course Line Commutated and PWM Rectifiers. Today we will be talking on AC-DC flyback converter. Um, this is basically we are now in the 8th week of this course. In today's lecture, we will primarily focus on this part of basic understanding of DC-DC flyback converter. The reason for this is because if we want to really understand the AC-DC flyback converter, we need to first understand the DC-DC flyback converter in a good fashion. Okay. And since this is an isolated DC-DC converter, which is usually not taught in first course on power electronics, at least in India. So we thought that we will first cover uh, the DC-DC flyback converter and then move into AC-DC flyback converter. Um, it will help us in understanding the AC-DC flyback converter in a much better fashion. So let us see the content of what we are going to talk about. At first, I will talk a little bit about transformer isolation and why we actually have a transformer isolation in the converter. In many applications, transformer isolation is mandatory as per standards. And in the previous week, we had talked about boost PFC, where we did not use any isolation. But now we will talk about these transformer isolated converters. While uh, while working on this transformer isolated converter, in precisely the flyback converter, we should also review what are the properties of high frequency transformers that we will use. Okay, there are some properties of these high frequency transformers which we utilize more as compared to traditional 50 hertz or 60 hertz transformer. The basic principle remains the same, but certain properties are used more in these kind of, say, flyback transformers. Certain properties, in particular, the magnetizing inductance, LM, is used more in these flyback transformers. LM is usually not very much used in 50 hertz or 60 hertz transformers, means low frequency ones. But this property of the transformer will be used extensively in this converter. And then we will go in depth of the flyback DC-DC converter, how its operation is and how does it work. And eventually this will be, then we will move into AC-DC flyback converter. Okay, and we will take up some design example. Okay, and in addition to these lectures, I would recommend that you go through Ericsson and Maximovich book on fundamentals of power electronics. This is a very nice book and is recommended to study from this book in addition to these lecture slides. Um, now, where is this AC-DC flyback converter used? Okay, now we have to understand now that since we have progressed in this course, we have to understand now that certain converters uh, are used at certain voltage and certain power levels. You must have realized this by this time that for certain power level uh, and what type of voltage, for example, single phase, three phase, whether the power level is less than 100 watt, whether the power level is around 1 to 10 kilowatt, or if the power level is megawatt, if the voltage is 230 volt single phase, or whether it is 400 volt three phase, or it may be 2.3 kV AC three phase. Uh, Depending on these values of voltage and power, our choice of converters actually change. Okay, uh, and certain converters work very well in at certain voltage and power levels, but it may not be optimum in a different voltage and power level, although it can theoretically work. So, taking this argument forward, we also are going to talk about the AC-DC flyback converters, which are typically, we see as of now, we see that it is typically, sorry, it is typically used at a power level of generally less than 150 watt. And um, it is an isolated power supply. Generally, AC-DC flyback converters uh, the AC, AC-DC flyback converters generally work in the power range of less than 150 watt, and we can see that it is generally used for many types of electronic power supplies, which are connected to the uh, wall socket. Okay, um, it has wide application areas in LED drivers and consumer electronics. LED driver is a very important application of flyback converters. It's very compact, and so we will talk about these LED drivers. We plan to have an example on this later. Now, so the converter basically, we have seen a boost PFC. So now we have an additional transformer isolation between the input grid and the output DC, right? So we can say now that in boost PFC, what we have seen is that we had this thing where you had a converter here, right? And here was the AC grid, and here was the load. Okay, here was the load. But now, so this current which was drawn from the AC grid, this current here, this current had to be at unity power factor or close to unity power factor, and good THD of like less than 5% in this current. Now, in addition, in the flyback converter, so we have, so now this is the flyback converter here. So we have the load and we have the source here. Okay. What is additionally coming up here is a form of transformer isolation here. Inside the flyback converter, we have a isolation. Okay. So the input and output is isolated through a transformer. So now this is something which is many times it is mandated by the standards. Okay, and we will see why this is needed. Okay, so basically, as you can see here, the transformer isolation is mandatory in certain applications from safety point of view and required by standards like IC 61000 and IEEE 519. So what is this safety standard? So let us understand this safety standard a little bit more. Okay, what do we do here? Now remember that this grid, if you see here, this grid um, is coming from a three-phase AC. Okay. For example, behind this, whenever we see this AC grid, if you go back, you will see that this is coming from actually a three-phase supply. Okay. And where do we get this supply? We get this supply from incoming grid. Say we have an 11 kV by 400 volt transformer, and I am showing you the secondary of this transformer, okay, which may be connected in star. Now this star point of the transformer on the secondary usually is earthed, okay, through maybe some form of a current sensor is there, okay, uh, so as to identify the fault current, but it is generally earthed through a low frequency resistor, like that, for sensing the fault current. Now this actually, if you now see, let me change the color. Now here this is forming the grid here, okay. This comes into the household, for example. Now one so this is how the circuit behind this single phase AC is. Now uh, how can a transformer give safety to the consumer, okay, or the user of this electronic item? Now suppose you are an user, so let me draw an user here, okay, who is going to use the uh, load. Okay, so um, this is a flyback converter. I'm showing you the total flyback converter. We are just focusing on the isolation part at first. So we'll understand this converter operation sometimes later. Okay, we'll talk about it, but I'm just trying to focus on the isolation part. Now, suppose you are an user, okay, you are working with the load, okay. So this is the load which is accessible to the user here, okay. Now, during your working, suppose your hand is touching this point, okay. It may happen always. Now, suppose you are standing on ground, okay. This is where you are standing. Your legs are on earth. Now, here you see, you can observe one thing, and that is that in spite of the fact that your hands are getting connected to some part of the circuit, under ideal condition, okay, when you have full isolation from the transformer, nothing, so then no current can flow because there is no closed path for the current to flow. You can observe here is that current cannot flow, no current can flow, because the primary and the secondary of this particular converter, okay, the input and the output is basically isolated, okay. So in spite of the fact that your legs are on earth and your hands are touching on the secondary side of the transformer, some part where you are connected the load, suppose you are turning on a TV, so this converter is supplying to a television, and you are touching some parts of the TV. Ideally, you should not get any shock, okay, because there is no path for the electric current to flow because of the transformer. Okay, so this is one of the very important use of transformer isolation because it gives safety to the user. Okay. There is also, of course, there is another very important use of transformer because it can step up or step down the voltage. But the second very important use of transformer is the safety and isolation. Now, if you can understand clearly that if there was no isolation, if this isolation was not present, and suppose you had connected, so suppose you were standing here and you connect your hand to this point here, then, and if your legs are basically your legs are earthed, okay, you are standing on the floor, then in fact you can see there is a path for this current to flow because this point and this point are at the same potential, right? Of course, there will be some impedance on the line, okay, yeah, because there is a not. But if we do not consider the impedance of the cable or this one, then there is a possibility of a current to flow on the primary, if you can. touch it on the primary. However, the primary is uh, nicely encapsulated the inside the transformer or inside the casing of this converter, and so you will not be able to usually access the primary side. And on the load side, even if you touch, ideally, you will not get a shock. So this is one of the important points what one should remember when we are talking about isolation inside converter. Okay. Now, having understood the purpose of the transformer here, so this is one purpose. Of course, we will have, as you can understand here, there's a 1:n transformer. Um and this 1:n transformer, of course, will then we expect that there will be some voltage conversion in this transformer as part of the operation of the converter. We'll talk about it later. Okay, the other point here when we talk about this is the power handled by these transformers is low, right? We have already said this this converter generally handles about like less than 150 watt, typically less than 100 watt, many applications. So since the power is low, actually the transformer here can operate at several tens of kilohertz. Okay, instead of the grid frequency. So far, in many of your older courses, you have studied a transformer being used at the 50 hertz or 60 hertz. That is the grid frequency. Here, we are operating the transformer at several tens of kilohertz. It is very common to have these flyback transformers in excess of 50 kilohertz. Okay, like 100 kilohertz, they can operate. So this is one of the important changes that we will see. And the size of the transformer is inversely proportional to the frequency in which it operates. Okay, so when we go for a higher switching frequency, like tens of kilohertz, the size of the transformer goes substantially low, okay, as compared to a 50 hertz transformer. So as you can understand, our application, for example, we are building a power supply for a television, and that means it must be very compact and it must go at the back of the screen somewhere there. So we must actually try to reduce the size of the transformer. And so instead of having an isolation at the 50 hertz, we could have isolated here also. We could have had a transformer here. Okay, but we do not do that. Okay, we will not use a transformer at the input because we want to reduce the size of the transformer. This is an important observation. Okay, the last thing that I would like to emphasize, although here we are talking here AC to DC, but okay, we'll talk about it. One of the important things is that this transformer here is for a DC-DC converter will work with square waves and it will not work with sine waves. That I will talk about sometime later. Okay, as I can tell you, the turns ratio of the high frequency transformer can be used to achieve large step down or step up ratio for optimum operation of the converter. Okay, we will use this 1:n, okay, to step up or step down the voltage, and this is needed for because we want to make the this whole converter, the power electronic part of it, the power part, the electronics part of it, the diodes, transistors, capacitors, we would like to operate at an optimum efficiency point. Okay, so this 1:n selection is also important from that point of view. Okay, now let us briefly review the properties of this transformer. Okay, uh, now in an ideal two-winding transformer, what we see is that, so we have shown you now an ideal two-winding transformer. So we have a V1 and V2, I1, I2, and the currents are entering the dot terminals, And here the relationships are V1 by N1 equal to V2 by N2, and I1 N1 plus I2 N2. This is coming from the MMF principle. Uh, I1 N1 plus I2 N2 equal to 0, right? Uh, Note that we sometimes use the current like this also, which I can give a new name, say I2 dash or something, where I2 dash is nothing but minus of I2. Okay, sorry, just a minute. Okay, so I2 dash is minus of I2, right? The direction is the other way. Okay, remember the dot convention. The dot convention says that um, um, at the dot terminal, both the polarities V1 and V2 are identical. So that is the one property of the dot terminal. And the other property of the dot terminal is that if I1 enters the dot terminal, so if current enters in one dot terminal like this, another current from the secondary side will go out of the dot terminal. Okay, this is the property of dot terminal. Okay, so if current enters through one dot terminal, and the other current will go out of the dot terminal. Okay, this is very important. And this ensures that under perfect condition, the power input is equal to power output. You can understand here that V1 I1 is equal to V2 I2. Okay, power input is equal to power output. Now you may argue that, okay, V2 I2 dash, okay, V2 I2 dash. So one side is input, one side is output. But here we will say that V1 I1 plus V2 I2 is equal to 0. Okay. But here I have taken, in this first equation, I have taken V1 I1 equal to V2 I2 dash. So this comes from the energy point of view, that power in is equal to power out. Whereas in the second equation, V1 I1 plus V2 I2 equal to 0, this comes from the two-port convention, which we are going to use. Okay. In two-port convention, the we have seen, you can see here this plus, and this will be, the current should enter both the ports, right? So we are going to go with that. And that is why if I just now remove all the other things, we will just say that this condition is what we come from the two-port network convention. And I will not any further use this one, and we will go with this convention. Okay, but you have to remember and kind of like uh, 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 match your understanding with the convention that we are going to use further. Okay, now when you do this, one of the important things is the primary and secondary MMF cancel each other at all points of time. Okay, this is an ideal transformer. So it means that if you have, so this is the core of the transformer. Okay, and you have a primary winding and you have a secondary winding here. You have to understand that the primary MMF and the secondary MMF, which are acting on this magnetic circuit, this will cancel each other at all points of time. So that is why I1 in 1 plus I2 in 2 equal to 0. Okay. And so the net flux which is flowing in this is 0 in an ideal transformer. Okay. In a practical transformer, this is not true. And the reluctance is 0. Okay, reluctance is 0. Okay, reluctance is 0 and permeability is infinite. So you need vanishingly small flux. Okay, in a normal transformer. Okay, the primary MMF and the secondary MMF, they are acting in opposition. Okay, So they cancel because they're acting in opposition. Why I am stressing this thing is that in a flyback transformer, this will not happen. So one must understand the difference. Uh, in a conventional transformer, the primary and secondary currents are flowing at the same time. Okay, I1 is flowing and I2 is also flowing at the same time, and therefore their MMFs will try to cancel each other. This is the principle of the transformer operation. In an ideal transformer, they will perfectly cancel each other, and so the net flux in the transformer is zero, or we can say vanishingly small to zero. Okay, the correct word is vanishingly small to zero. And the reluctance is zero and the permeability is infinite. So we will basically need infinitely small flux for the energy to transfer from primary to secondary. So since the flux is zero, therefore energy in the core is also zero, right? There's no flux actually in an ideal transformer, or very small flux. Okay. Uh, so this happens in an ideal transformer, right? On the other hand, suppose if we take an inductor, okay? So in an inductor, what happens is, so you have a winding like this, okay, and like this, okay, and there is no secondary MMF like that, okay. So there is one coil which is wound on the core of the transformer. So the core may be like here I have shown rectangular, but it can be a toroid also. But the purpose of the inductor is different. The purpose of the inductor is it is designed to store the energy in the core. Okay, so we want some energy to be stored in the core of the inductor, which we will recover at some other point of time. But on the other hand, if you see the transformer was not designed for this purpose. It was designed so that the flux in the core is vanishingly small. So whatever energy comes from the primary winding, we will immediately at the same time extract it from the secondary winding, so that the instantaneous energy in the transformer stored in the core is negligible. But in an inductor, this is not true. Okay, inductor is supposed to store the energy. Okay, so that's what I said. The transformer is designed so that in, yeah. Okay. But the now comes the slight modification which happens in a flyback transformer. Okay, the flyback transformer basically acts like an inductor. Okay, and it will store energy like an inductor. Okay, in this one. So what happens in a flyback flyback transformer? We actually use two switches here. So a flyback this is the flyback transformer, but we are going to use switches here so that we will store the energy at some point of time using one of the switches, and we will retrieve that energy from that transformer by using the other switch at some other point of time. Okay, so the flyback transformer here will act like an inductor. It is a transformer, but we are making it to behave like an inductor. Of course, it has galvanic isolation. You can understand that we have the galvanic isolation between the primary and secondary, like a mutually coupled magnetic circuit. Um, but this will be working. Okay, this transformer will work like a inductor. Okay, how will it work like an inductor? So let us see. mm, that okay, I will come to this. Just hold on for a second. We will, yeah, we will come to this a little bit later, how it will work as an inductor. So, but the principle is that the transformer here, although is a transformer which has a primary and a secondary, but it will act as an inductor. Okay. Now, first, thing is that in a practical transformer, so let us see the various non-idealities. Okay, in this case, the non-ideality that plays a very important role is the magnetizing inductance Lm. Okay, so we have seen in conventional transformers, we model it like this way. Okay, you know this one, I'm just repeating. So this is the Lm, okay, and this we have R1, and this we have X1, and this here is X2 prime and R2 prime. Okay, so this is a very standard form of transformer. Now, in some cases, we take the secondary on the primary side and we just write it like this way. Okay, or just hold on for a second. Yeah, we can also do it like this way, or we can do it like the other way. Okay, this way we can actually model the transformer, whether we take the whole impedance on the primary side or the whole impedance on the secondary side, right? Um, but in this case, in this flyback transformer, this inductance Lm, this actually plays a very important role. Of course, there are leakage resistance and inductance. Okay, leakage inductance is there and resistance is there, but their role is minor. Okay, and of course they have a role to play, and at the end of this lecture I will show you what is the role of this leakage. I'll show you one example, but it has a minor role to play during the transient. Okay, so during the normal operation their effect is not very important. Okay, so so we will actually, in our circuit, we have actually removed this R and L, and that is why in our circuit you can see we have only kept Lm, okay, neglecting the effect of all the other resistance and leakage inductance. So this is the model of the transformer that we will use. So if we take this model, what are the governing equations? You can see here, if you apply KCL at this point, then we have this equation I1 is equal to ILM plus I1 dash T. Okay, this is the equation. And this part of the transformer, which is represented here, okay, this part you can see here, this part is the ideal transformer. Okay, this follows the perfect MMF equations like I1 dash into N1. So I1 dash is this current. I1 dash into N1 is equal to I2 into is equal to minus I2 into N2, or we can write I1 dash into N1 plus I2 into N2 equal to 0. Okay, so these are the perfect transformers or ideal transformers equation. V1 by N1 equal to V2 by N2, right? Yeah. So now this is the, but then this Lm comes into the picture, and the Lm is taken care by this equation here. Okay, the current which is ILM is flowing. Now this Lm or the magnetizing inductance has properties which are following the property of an inductor. Okay, and because we are trying to represent, as I told you, this transformer is going to store energy, right? And it will store energy for some point of time. And because we are going to also use switches along with this transformer. So it will store energy at some point of time and it will deliver energy at some other point of time. So therefore, and this stored energy is basically stored in this inductor, because this part here, okay, this part is ideal. Okay, so this part is ideal. So it cannot store the energy. What is stored here is the non-ideal part, and this part will store the energy. Okay, so this you have to remember. So if this is going to store the energy, it is like behaving as an inductor. So the equations, it will follow the equations of an inductor. For example, this is the first equation which we know, V equal to L di dt. That is the main equation of an inductor, which will be followed here. Of course, here the value of Lm is constant. So Lm is constant, which we will follow. Okay, and this will follow because the core is not saturated. We will not saturate the core, and so we will assume that Lm is constant, right? And yeah, yeah, and of course we can also understand that if Lm is high, then the current which is flowing ILM, that will be low. Okay. The other important point is coming here. Okay. Now the input voltage, that is this V1T. Okay. This voltage V1T, it should have zero average value or zero DC value. This is an important observation. Okay. Uh, So if we give this V1 voltage, most of the time you will see that in a DC-DC flyback, we will give V1 something like a square wave, okay, like this. But remember that the square wave should have zero DC. So this is the V1T, okay. This is uh, one of the things that you should note. So far in many of your previous courses, you have assumed that the input voltage is sinusoidal. Okay, because the grid is sinusoidal, so we have seen a 50 hertz transformer operating with a sinusoidal source. But in this DC-DC flyback transformer, the voltage is not sinusoidal. In fact, it is a square wave. Okay, so that's why I have drawn a square wave. Okay, so, but the transformer will operate nicely with a square wave also. This is sometimes a little bit difficult to comprehend, but a transformer can work equally well in a sine wave as well as in a square wave. So there is no issue about it. Okay. So this voltage here is going to be a square wave V1T. That is what I have shown here, V1T. The important point here is that it should have zero DC. Okay. Now, what will happen if there is no, if there is a DC, what will happen is, like you can see here, let me draw the current ILM. If you apply this DC, so we'll take this one. So what will happen to ILM? ILM will, when you put a DC, you will see that this is going up and this will go down. This is going up and this is going down like this. Okay, this is the ILM, the current flowing through the inductor. Okay, it will go up and down like this. Right? Now, if the input V1T voltage does not have a zero value, what will happen to this current? Okay, suppose I take the condition when the average value is not zero. Okay, so what will happen is it will start from zero, increase, okay, and it will come back, but when it comes back, it will not come back to zero. Okay, it will not come back to zero. Then what will happen next time when the positive voltage comes, it will again rise, but not come back to zero. Okay, it will again rise, not come back to zero like this. So what are you observing therefore is that if you do not, if you're zero, if you do not have a zero DC or if you have a finite DC, okay, the current will go on rising, ILM current. And at one point of time, you will see that your transformer is getting saturated. Okay. So if it gets saturated, then the value of LM will fall. Okay. If once the transformer saturates, the value of L will fall down. Okay. And so this is something which we want to avoid. Okay. So this will should have the input square wave should have a zero DC or average value. Thinking it in other way, if it has a finite DC value, some finite DC, then this transfer, this impedance of the inductor at DC will be zero. And so a DC will flow. Okay. If you have a DC, the impedance of the inductor is zero at DC. so a current will continuously flow. Okay. Of course, you may argue that, okay, who will limit the current, right? So basically, there is also some resistance also there, but yeah, that is what will limit this current. But we will not talk about that resistance. So we will say that basically V1T will be should have zero average value. Okay. Now, one of the things for this transformer is also is the what I should say, mm, the BH curve. One has to understand a little bit about the BH curve. So if you have, this is an inductor, and so there is a core in this transformer, and the core is usually made up of a ferrite, okay, which has this kind of a BH curve of the ferrite or some other magnetic material. They will have this kind of a BH curve, right? So when you have um, uh, H, which is going high. So when you allow the current to flow in the winding, basically you are creating a magnetic field, right? When the current is flowing, you are creating a magnetic field, and the magnetic field intensity H therefore increases, right? But if it increases beyond a certain point, it will follow this curve. And when it increases beyond a certain point, for example, up after this point, then the core starts to saturate. Saturate means the flux density or the flux in the core can no longer go on, keep on rising, right? So the core will saturate here. And what happens now, you have to understand that when the transformer gets saturated, the inductance becomes smaller in value. Okay, why does it happen? Because you can see basically the slope of this curve is proportional to Lm. Okay, the slope of the curve is proportional to Lm, because you can derive this. I'm not going to derive it here. So L can be written as a proportionality factor of B by H with some constant here. Okay. Uh, So mm, basically the slope here is high. The slope is high in this linear part, okay, and it's constant. But at this point here, okay, in this region here, okay, in this region, the slope is falling. And that is why the L value, when the transformer saturates, will fall down. Now, this has a lot of consequence in the operation of the flyback converter. And we would not like to have a variable L in those all the equations and all the waveforms. That will make things very, very complicated to analyze. So we would like to have L equal to constant. Okay, and therefore we would like to work in this region where the slope is constant. Okay, we'll always try to work there. We do not want a saturation in the so therefore we would like to the transformer to work in the linear region of the BH curve. Okay, one of the important things that we will also observe later is that this has some connotations. We work in with air gap or powdered cord, okay, with a high reluctance, so that it does not saturate. Okay, we will talk it a little bit later, but just keep in mind, we usually work with transformer with air gap. Either we put a physical air gap or we work with a powdered cord. Powdered cord means it is a um, special type of cord in which the air gap is distributed throughout the body of the material which is using this one, okay, which is made to use the core. So it is the air gap is uniformly distributed, and so therefore, so the transformer is prevented from getting into the saturation region. Okay. Of course, you can now have a three-winding transformer. In fact, flyback converters are actually this flyback converter is very much used for in real life very much used for getting multiple output voltages. Okay, many times if you see a flyback converter, it will have one primary and two or three secondary windings. Okay, so your input voltage like maybe 100 volt, and it may be providing you 12 volt and 5 volt. Okay, this is very common in flyback converters. So it will have then a three winding transformer, right? And this will also follow the same equations like this. This is the same equation, but now it will have the third term. But the magnetizing inductor will also have this V1 equal to LMD INM. The equations remain same, but we will have another term coming into this picture. And we will not talk much about three winding transformer because three winding is just an extension of the two winding concept. Okay, so we will not talk about it. Now, let us understand a little bit about what happens when we connect switches on these transformers, right? Now, this here comes something interesting. Okay, here is where a transformer will start to behave like an inductor. Okay, and we'll see how this transformer is going to store the energy in that LM inductor, which is basically the body of the or the core of the transformer. So let us get a condition where we have two switches, S1 and S2, and S1 and S2 are used in a complementary fashion. Okay, so if S1 is on, S2 is off, and vice versa. Now see, suppose we have this transformer here. Okay, we have this one. This is the core, and here is the primary, and here is the secondary, and we have one switch here, S1, and one switch here, S2. Okay. Now, now when S1 is on, right? What will happen if S1 is on and S2 is off? What will going to happen is, remember, this part of the transformer is ideal transformer. So if S2 is off, I2 cannot flow. I2 is not flowing. Therefore, I1 dash cannot flow. Okay. I1 dash cannot flow because this is an ideal transformer. It has to maintain the MMF equation. And so I1 dash N1 plus I2 2 into N2 should be equal to 0, right? So here I1 dash cannot flow because I2 equal to 0, right? So therefore, whatever current flows through I1 must flow through the inductor LM, right? So when we have turned on this switch, the energy is basically getting stored in this code. So let me draw with a different color. Um, so the energy is now getting stored here, okay, in the form of a flux. Okay, you have turned on S1, S2 is off, and the energy is getting stored in the uh, code, right? Now current is of course flowing in the physical primary winding. Current is because this is on, so some current is flowing here. Okay, but no current can flow on this secondary winding. Okay, no current can flow, right? So here under this condition, I2 is equal to I1 dash, okay, equal to 0, right? No current is flowing, and I1 is equal to ILMT. And since we have applied a finite DC voltage, we have to follow the behavior of the inductor. And so the current which is there is governed by the equation V equal to Lm into dILm by dt. And so what will happen is, because we have given a finite voltage, so the current will increase, and therefore the flux will increase, and the energy being stored will go on increasing in time, with time, inside the core of the transformer. Now let us see what happens when we go the other way. Okay, when we are going to get we make S1 off and S2 on. So now we are going to turn on this switch. So let me draw it once more. Okay, we have already stored the code. Now we have turned on this switch like this. Okay, the current has started to flow, right? I2 can flow due to the load, and since I2 is flowing, okay, therefore I1 dash also must flow. But now what we have done is S1 is open, so therefore I1 cannot flow, right? Because S1 is open. So therefore, what will happen is ILM, this current which was flowing, will now flow like this way. Okay, right? And so uh, the basically the magnetic flux will start to decrease. So basically you had already stored some energy in the form of a flux, okay, in the core. That flux will now start to go down. Okay, basically the core will now release back this energy into the secondary winding. The flux will fall, and you can see it is exactly following the dot convention, because the current is now uh, yeah, like this. It is going out of the dot terminal, so this will flow like this. Okay, so magnetic flux should decrease in the core of the transformer. And one important point here is that S1 and S2 must be operated in such a way at steady state. Here is the important point. The steady state, uh, the net change in the flux should be zero every switching cycle. What does this mean? It means the starting point or the starting magnitude of flux and the ending magnitude of flux after you have turned on both the switches, S1 on and S2 on, the initial magnitude and the final magnitude of the flux must be same. If you don't do this, then what will happen is the flux will go on increasing after every switching cycle, and eventually you will saturate the transformer, and then there is no use of this one. So we do not want the saturation. So therefore, we will say that the net change in the flux should be zero after every switching cycle. Okay, the flux should come back to where it started, right? Okay, so this is the important observation when you work with two switches inside the flyback transformer. Okay,